All right, perfect. Yeah, so my name is Kaley Brauer. I'm a PhD candidate at MIT, and I'm excited to be sharing this, I guess, teaser trailer of the project we've been working on right now. This is ongoing work, so I'm just kind of giving an overview of the data we're hoping to be getting through this simulation project with all these wonderful collaborators here. And this is the Aeos project, is the name of it. And our goal is to model galactic chemical evolution in dwarf galaxies with a focus on individual stars. So looking at stellar feedback and metal mixing as a result of the individual stars in these galaxies. And so, the old stars in these really faint dwarf galaxies provide a snapshot of the first stages of chemical enrichment in the universe. And so, we've seen a fair number of the surviving ultra faint dwarf galaxies around our own galaxy. So here's, just Reticulum 2, for example. But also, of course, these faint dwarf galaxies accreted into the Milky Way and are kind of the building blocks, so the metal pore component of our stellar halo. And so if we want to understand, their evolutionary histories, understand our own Milky Way formation history, it's vital to understand, how these dwarf galaxies evolved, to learn about this galaxy formation, early star formation, and the nucleosynthetic processes that formed all these chemical abundances in the stars we observe. The problem is that the current state of dwarf galaxy chemical evolution models are just insufficient to begin to describe all the data that we're getting now. So we're getting all these observations of stellar abundances in the halo, in the surrounding dwarf galaxies. And this impressive amount of data has actually outpaced the models for how these stellar abundances formed. And just for example, a lot of these models have simple parametric models for the inflow and outflow of the gas, or assume instantaneous homogenization of yields and capture only the mean abundance evolution. So that's just some of the current state-of-the-art galaxy chemical evolution models. And in particular, these latter 2 points mean that these models are largely incapable of modeling the abundance scatter that we are observing in stars these days. And so we wanted to help address that by focusing on, a more detailed dwarf galaxy modeling, especially with we're like every day we're getting more and more computational resources and, these more and more powerful supercomputers, so we can start actually tackling these very difficult models without the need to make as many assumptions as previous simulations have done. So this is the Aeos project that we are working on now. And it's just about the name briefly. So it's from Greek mythology with the Helios sun chariot that pulled the sun across the sky. One of the horses was called Aeos, he who turns the sky. So that is the Aeos project that we are currently working on. And what the simulations they are high resolution cosmological hydrodynamic simulations. This is just a picture of one of the parent simulations that we ran in dark matter only to get like an idea of the formation before running the more detailed, baryonic physics models. And the important part is what makes Aeos different from other models is really this focus on the detailed treatment of stellar yields. And as I've mentioned, stellar feedback and metal enrichment from individual stars, where in some of these dwarf galaxies, that is very important for getting, both scatter within galaxies. And, if we want to have direct comparisons to like star by star observations of metal pore chemical abundances, we want to be able to see the feedback at this level. And just some quickly, some of the technical overviews of the simulations. We're running it with INZO, this adaptive mesh refinement code that several of our collaborators who are working on this project also helped develop. And our fiducial cosmological simulation is a 1 megaparsec box, dark matter resolution of 1840 stellar mass, and all of our models, all of our simulations are being run from a redshift of about 130 down to reionization about redshift 7. Not continuing past that or not planning to continue past that, both for practical reasons, it's just the simulation slow considerably, and also we're focusing on these dwarf galaxies that form the bulk of their stars prior to reionization. So we're planning to stop around there. And we're going to do the fiducial model both with and without pair instability supernova to see the effects of that on early galactic chemical evolution. And in addition, we're running 3 zoom simulations of dwarf galaxies of 3 different sizes. So we picked out 3 different dwarfs from the parent simulation and ran each of those in much higher, or currently running those with a much higher resolution on each of those to see both galaxy to galaxy scatter and see how, at which mass levels and time scales this star by star formation seems to be most important. And in the simulation, we trace 8 metals, these here. And so those are the detailed chemical abundances that we get in our individual stars. And so there are a number of science questions that we are hoping to answer with these simulations once they're finished. Just to briefly mention a few of them, one of the biggest questions is, how do metals mix in the interstellar medium of dwarf galaxies at high redshift? Because that's where the metal mixing is where a lot of assumptions are made in other simulations. And so if we're trying to really, do the really high resolution with the feedback of these individual stars, we want to see how the metals are mixing and how that's affecting the chemical abundances that we are going to be observing in real stars. And in addition, we're all very interested in galaxy evolution. And so we want to know what information about early galactic galaxy evolution is contained in the spreads of stellar abundance patterns that we can observe today. So, using the simulations to draw those connections and see what we are able to learn from the data that we can obtain now. And then just one additional one is, so we want to see how this new treatment of the star by star treatment with the high resolution around each individual star, how that affects galaxy formation in simulations. So actually along that vein, we are comparing to the Birth of a Galaxy simulation that John Weiss ran in 2012. And so we have the same initial conditions as this other simulation. And we want to see how this, this treatment that we're running now affects the simulation. And, once again, at what, how important this more detailed treatment is, or if we can continue making many of the assumptions that were made in previous simulations without losing that much information. So we want to directly compare those. And so along this vein, actually, we have very preliminary results. So definitely take this with a grain of salt, but this, I think it's actually from yesterday. But Jennifer Mead, who is a first-year Columbia PhD student, has already started comparing the Birth of a Galaxy to the Aeos simulations. And right off the bat, so I guess I'll say quickly, so this is just the cumulative star formation history of the simulations so far. So Aeos is still running. But we're already seeing some differences. So the dotted lines are our simulations, the Aeos simulations. And you can see here in red is when
2 minutes.
Oh yes, thank you. The red is when the pop 3 stars form, and we're seeing them form, there we go. We're seeing them form a lot earlier than in the Birth of a Galaxy. And we're also seeing a delay in when the pop 2 stars start. So, once again, very preliminary. We'll actually see what is causing this. Some initial thoughts we've already said, maybe due to, we have a little bit of a lower Lyman-Werner background. There could be these differences in stochastic yields and mixing, or even the definition of POP2. So definitely need to stay tuned to see if what is actually going on and what differences we ended up finding after, rooting out all the other causes. So yeah, simulations and analysis are ongoing, and we'll hopefully have more information about that after, we finish running everything. So yeah, I'll, just kind of leave up my overview, but this is just a quick description of the simulations that we are currently running, still several months out. But these are hydrodynamic cosmological simulations of dwarf galaxy evolution with stellar feedback and metal enrichment from individual stars, with this focus on metal mixing in the interstellar medium, and using this as a way to inform our interpretation of all these observations that we're getting, and to probe what we can learn about early galaxy evolution and star formation. So thank you.
All right, thank you very much, Kaley. Do we have questions? I'll go ahead and ask a first one. So you currently are running them to Redshift 7. Is there any, I'm sure it's computationally expensive, but is there any hope of extending that to like Redshift 2 or 3, perhaps when a lot of these things might accrete into higher mass halo, like, for the Milky Way, we think Enceladus fell in around Redshift 2, to see what the extended star formation history will do there in terms of the abundances.
Yeah, that would be really interesting to see. It definitely, after even Redshift 10, the simulation just starts slowing such significantly that, I guess it's a little bit dependent on if they'll continue giving us supercomputing time to see how long they'll let us run it before we have to pull the plug. But I would love to continue running it as long as possible. But realistically, we'll probably get to 7. And then if we have a compelling reason, it would be nice to push it farther as well.
Gary?
Hi, Kaley. Good talk. The question I had is that from what you looked at, it didn't seem as if you had any R process nucleosynthesis. Is that simply because you don't expect much to happen in terms of neutron star mergers before Redshift 7 or what?
Yeah, so we were going to use some of the barium as a tracer, but yeah, it ended up not making the cut of the traced particles, which is a shame. But yeah, we're also not sure that like on our list of like comparison priorities, it wasn't one of the top ones because each additional field did add additional computational expense. But yeah, I would be interested to see that as well because I'm also very fascinated in early R process enrichment.
Okay, thanks.
We have a question from Sarah in the chat here. Since you're using a cosmological simulation as your starting point, is the missing satellite problem an issue, i.e. the number or mass spectrum of the dwarf galaxies?
Yeah, I guess we haven't seen that. So in the like dark matter only parent simulation, I do believe that was like that. I didn't check the number, but I would expect that to be an issue. But with the full hydrodynamic simulations, it's been working itself out. I need to check actually to see the number of satellites, but once you start having like the full like baryon and like having like disk potentials and things like that, a lot of those get disrupted, and so then I haven't seen that be an issue in the previous simulations we've run.
All right.